Hello everyone, welcome to webinar series on FPGA. So we are from Logictronics and Digitronics Nepal. So welcome, and many attendees are still waiting and they are joining on. So let's wait a bit time for them to join. And basically this session is on writing VHDL Verilog design systems. So in this session, we're going to talk about how we can write systems with like a number of structural modules in VHDL or Verilog. So this session is organized by Logictronics and Digitronics Nepal, and I am Krishna Gairi, your host, and I represent Digitronics Nepal, and I have presenter Jagannath Paudel for presenting on the hashing function, how to get higher hash rate on a hashing function. So we will like to start the presentation. So basically uh, we already have talked about the basic outlines of this session. So in this second webinar session, we are going to talk about how to write the hash functions and basics of encryption and decryption. So basically these things which we are going to talk on. So let's go to the table of contents. So in the first we have very basics of VHDL and Verilog. So we will talk about the hardware description language, SDL, VHDL and Verilog. Then we have the structural design methods, little bit of structural design method in VHDL and Verilog, and we will talk about the how to get highest hash rate on a crypto algorithm, and we will talk about that in the third. And in the fourth session, we have writing AES encryption and decryption modules in VHDL and Verilog. So these are the basic outlines of our session. So we just have started. So this is the table of content, and now we are going to start with the first topic, which is basics and insights of VHDL and Verilog. So basically, you guys already know about the VHDL and Verilog. So these are the hardware description language. So basically, VHDL stands for VHSIC, hardware description language, which is very high speed integrated circuit hardware description language. So we have the insights of VHDL and Verilog and the structural design method in few slides. So as I told, so hardware description language are heavily preferred for FPGAs and the logic arrays. And in the first development of FPGAs, um, they are just called as glue logic. FPGA are just called as glue logic because they only have few logic gates and number of logic gates. But nowadays the FPGA's architecture is quite changing, and it is like is the heterogeneous chip inside lots of things. So like it consists of the different logical units, different high speed interconnects, and it also consists of some processing elements like the processors. So FPGA is now becoming the heterogeneous chip, so it is heavily preferred for different type of designs, systems, embedded processing unit, and high-speed signal processing units. And the you already know that the application of FPGA is from the basic embedded computing, edge computing, to the defense equipment and satellites. So here we have the hardware description language design flow. Basically, SDL design flow is the way of how we can start and how we can complete the process of writing and implementing any algorithm on FPGA. So basically, we did the architectural design in the first section, then where we write the problem identification, and we write the basics of solutions, so algorithms and the ideas about will be brainstorm here. And in the next we have the SDL design entry. So in this SDL design entry, we will write the hardware description languages, and at the next session we just have to run the simulation, behavioral simulation. So this simulation is actually the platform where we can realize the real-time environment So basically simulation is virtual environment, so we can simulate and we can verify our logic, basically logic or SDL programs. So there are lots of SDL simulator, like you might familiar with the model sim, you might familiar with Pivado or IAC simulator, quarter simulation tools and other tools. So basically simulation gives us early idea about how the algorithm or how the SDL code is working on. So simulation help us much to estimate the overall outcomes of the module, so we can plan for the next phase. So basically in the next phase we have synthesis process. So synthesis process is actually the process of checking the syntax, semantics, and verifying the general code by the tool. So synthesis process checks everything. So it also generates the netlist, or basically synthesis process can also generate, or the process will create the RTL schematic also, so we can get the overall netlist, means how the logic units will be connected on, etc., in the schematic. So next step is the implementation step. So in implementation steps, the mapping and the planning process will be done. So basically IO mapping, IO planning will be done in this implementation. So the logical ports in the hardware description language programs or VHDL programs or Verilog programs, logical ports on those programs will be connected with the physical one. So physical means the hardware based ports. So basically FPGA have the hardware based ports. So physical program, physical ports will be connected with the logical ports. So this is the process of implementation. So next step is the timing analysis. Timing analysis stands for checking the timing behavior. So is the code is meeting the timing requirements or constraints. So if the code or the module or the algorithm which is implemented on hardware design, hardware description language design is meeting those things, then the bit stream generation can be performed on. So bit stream generation generates the bit file. Actually, bit file is the combination of hex codes. So this bit file can be uploaded to the FPGA or the devices, or basically the array devices, like is the any specific vendor based FPGA device. So then we can realize the overall algorithm on hardware. So this is the very basic hardware description language flow. So this is generic flow. So most of design methods or design on FPGA follow this flow. So if you are using, if we are like implementing algorithm on FPGA or such type of devices, programmable devices, then you will use this type of flow. So let's go to next one. So in the next one, what we have is we have the basics of VHDL. So we can understand what the VHDL is and how VHDL works. So basically, VHDL stands for VHSIC. VHDL, as we talked earlier. So it is standardized by IEEE in 1987. So there are a few packages like the library files on the C, C++ languages. So there is IEEE 1164 package, which is for data types like integer float data types in C, C++. In VHDL, we have standard logic, we have integer, we have bit, and there are vectors also. So there are a few data types, and 1076.3 is for numeric, and 1076.4 is for timing packages. So these packages can be instantiated at the top and can be utilized for calling different functions. So this is the very basics of VHDL, which you already familiar with, and we have here one example, very simple example, and this very simple example is on the OR gate. So very simple one. So let's see the basics of VHDL program. So at the first top of the program, we have the library section. So the OR gate is implemented on VHDL. So let's see how it works. So at the first we have library, library IEEE is called here. So this is for like defining the entity and architecture and keywords, and we have the standard logic 1164.all. This standard logic 1164.all is for instantiating or the, defining the data types standard logic. So standard logic is type of data type in VHDL. Second section is entity. First one is library. Second is entity, where we define the ports like it's integer A, B, C, D in C, C++. So we have the entity, and here we have the orientation of ports. So these are a little bit different than high-level programming languages. So third section is architecture, where we actually realize the logic. So this architecture is the main part where we do the processing things or assignments. So architecture name of entity name is this is the syntax. So architecture begins, architecture ends, and between that begin and end we have the main assignment. So here we can see y less than equals to a or b. So this is the very basic logic operation of or. So in VHDL. So let's go for a little bit next one. So in the next we have the structural design method on VHDL. So basically, while we want to design like complete or the complex design modules, design systems or projects on VHDL or Verilog, we need to know about structural design methods. So structural design method stands for how we can integrate, how we can develop small units or modules and integrate those modules on single one. So basically, we have here one example of creating the half header. Actually, this is also simple, very simple. We just want to make you clear about the structural design methods. So this is the main objective of this slide. So we have one example of creating half header. So you can see there are two library files, library IEEE and 1164.all, and we have the entity section where we have all the ports, port A, port B, carry, and so on listed here. And we have the architecture section. So in the architecture section, we have the assignment operation. So assignment is on here. So we can see sum is less than equals to, actually less than equals to is the assignment operator. So it actually did the assignment. So what that means is A XOR B will be, the result of A XOR B will be sent to the sum. So this operator did the assignment of right hand side result to left hand side operand or the port or the signal. So basically we have another port or the output carry less than equals to A and B. So this is the basics of half header. We are not talking specifically for half header. Actually, we are going to utilize this half header for full header design. So let's see the full header implementation here. So we just want to call this half header module. So we just represented half header in box or the block. So we just want to call this half header in like a full header module. Then we have to have similar type of structure of writing VHDL programs. So we can see here we have the block design of full header where we want to have half header. So let's see the entity section. Entity section is the port declaration section where we declare our A of B of C in 3 inputs and the C out and sum of for sum and carry. So these are the ports, and we have the next section. That means third section is architecture. Basically in architecture section, what we have is we have the component section. So basically this component section is the main thing for structural design. So component is the like calling or instantiating another module inside the top module. So basically now this full header is working as top module and the half header is child module. So we need to call this entity of half header inside the full header. So basically we just take this entity from entity to entity half header and paste here, and we just rename it as component. So entity is renamed as component and the module name is half header as usual, and we have the port, all the ports are same, and we close with in component. So this is the component declaration session. section. So after that we have the begin. Let's just forget this signal line for now. We have begin and we have another segment called component port mapping. So actually this is component section, and next one is the port mapping, component declaration, and we have the port mapping. In the port mapping, we just connect our top module or the in child module with top module basically. So we can see component name is here, component one. So we can place any name, and half adder is the module name which we have called on component section, and port map is the keyword for mapping the ports or the connecting ports of child module and top module. And we connected our port A with AF. Port A means half header A. So we can see the figure here. So half header A is connected with AF, B is connected with BF, and as usual, SOM is connected with S1. S1 is actually the signal. So signal is for like temporary storage or the connecting wires. So we have defined signal here, signal S1, C1, C2 with standard logic data type. So this is the way we connected the port mapping plan, or our port mapping section carries connected to C1. So we have the another actually a full adder can be built by using two half adders. So first half adder is instantiated here, and second half adder is instantiated here. So we just have to have one component of half adder here, and we can utilize number of mapping or port mapping of full adder using half adders. So basically we have one component and we have two different modules called in the main of architecture in full adder. So we have one half adder instantiated, and we just utilize that half adder in two times. So that is two times utilization. So this structural design method actually gives us or allow us to utilize the code multiple times. So this is the very beauty of very nice methods of structural method. So this is basics on VHDL. So let's talk about a little bit on Verilog. Actually, we just want to cover both of topics, both of SDLs. So we just also have the Verilog session. So we will talk about a little bit on the Verilog background. So basically, Verilog is also the hardware description language. So it is uh, built or it is actually developed around the development of VHDL. So Verilog is also utilized for FPGA design and VLSI design and verification. So basically, Verilog is standardized by IEEE 81364 number. So IEEE actually also standardized the revision of Verilog. So the last revision was 95 revision, and then after it is revised is a 2001 revision. The most preferred Verilog version is 2001. However, there are other two versions also, that is 2005 and 2009 of Verilog, and that 2009 version of Verilog is called System Verilog. That means Verilog is merged with System Verilog, so there is no separate Verilog revision of 2009. So it is System Verilog, and System Verilog is superset of Verilog. So 2005 version of Verilog is not much utilized. However, most of tools supports it. So you can write your Verilog program in 95 revision or 2001 revision or 2005 revision. However, we will show you the basics code on 2001 revision actually. Sorry, 2001 revision. So same thing. So we want to design on. So we have the OR gate with Verilog. So this is 2001 revision. We also have the comments, and Verilog comments are is the C comments, C programming language comments. So we have the module. Actually, module is a keyword or function name. Sorry, function, and the module space module name. So this is user defined. So we have the module name of OR gate. We want to design OR gate, and we just have bracket here, and we just list all the ports with orientation. So we have the A, B as input. So we have input A comma B. Actually, we place the small letter base ports. However, we have here capital letter base ports. So it must be followed that value is case sensitive and port name. So we must have same name here and here. However, we follow input small a comma small b comma output z. So the truth table is a little bit different than the instantiation here. However, you will just understand the things. So we have the OR gate with ports, these ports, and we have the assign operation. Assign Z equals to A or B. Actually, this bar is OR for OR operator for Verilog, so use it for uh, we use it for ORing A and B. We have the semicolon and we have in module. There is no semicolon in the last in module line. So this is 2001 revision of Verilog. So let's go for structural method on Verilog, actually, which is the main thing we want to make you a little bit clear on. So we have the structural way, same thing which we have talked already on. So this is the half header section. We have designed the half header and we have the full header. So full header actually calls the half header module 2 times, and Verilog module or Verilog codes are a little bit small or shorter, or the less lines or less code than the VHDL. Actually, VHDL need lots of lines for small programs also. Like if we want to design the logic gates, it will need all the things, library, entity, architecture. But Verilog is quite simple and quite easier. Actually, Verilog is a successor of C language, or we can relate Verilog with C language. So PHDL is successor of ADA language. So these are the things which can be understanding background of this language. So Verilog structural method is here. So basically we have the module name and we have the same port, same thing as we design on PHDL. So we have the ports here, input and output ports. We have the wires like signals in PHDL, and we have the half header. This is the module name half header, or the child module half header, label name HA1, and we have the ports. Ports are organized in the manner way how the like definition is carried on. So S1 C1 is passed through these inputs of full header is passed through the half header, and finally we can get the sum and carry. So sum is obtained from here and carry C out is obtained from here. So this is the very basic block design. So this is the basics of structural design, Verilog. So let's go to next one. So next is the most demanding session, which is how to get optimum hash rate using Keccak hash function, and how to utilize this Keccak hash function for getting 12 GHz or giga hash rate per second or higher. Here we are going to talk on few methodologies of using this Keccak hash functions. So there are a few methodologies which we are going to talk on. So we will talk about the how to get a highest throughput, optimize it, and reduce the critical path delay. So these are the main things which will be needed if you are interested on like hashing development, hash-based development, like is the crypto-based mining application development for FPGA. So these are things which you need to know. So I will like to hand over this session 3 to Jagannath Paudel. Now he will lead. So Jagannath, you can start with your presentation.
Okay, thank you, sir. Hey everybody, it's Jagannath from digitronixnepali, and today I'm gonna share with you how to how to get the highest throughput through any function you want. Okay, it's not just for cryptography or mining application, just for any you can use any function and get the highest throughput with the methodology that I'm gonna describe now. Okay, let's get started. Okay, so this is some. Let's get started with some basic thing. Okay, let's say you have got a function. We don't care what function is it, but let's say you have got a function. So this is the basic way of using that function, iteratively and getting the output. So we have got one input, and that input is passed through this register to this function for the first time, and after it gets input, then the output of that function is again fed into that function again in every clock cycle. And depending upon the algorithm or the output desired, this loop may be repeated like 10 times, maybe for some application maybe 20 times, 20 30 times. It depends upon the application. Okay, for a let's take for example of Keccak. Okay, in Keccak, this loop has to be repeated, iterated 24 times. So it will depend upon the algorithm. So what are the characteristics of this design? The first characteristics, it has the latency same as the number of loop cycles. So if it has got 24 cycles, then we have if it is repeated 24 times, then it has got latency of 24 clock cycles. So in case of Keccak, it's 24 cycles. And the main advantage of this design is it has got the minimum area, and throughput is also minimum because you have to wait 24 cycles until you get to input new value. So until the first output until we get the first output, we won't be able to input new input in this module. So that's its main disadvantage, and this is not desirable, of course, for a higher hash rate generation. So let's look at another module, another design. So this is another design, and in this case also we just give input through this demux, and we pass through the function, but this function is unrolled number of times, like maybe 4 times or 8 times, or of any number of times you want. You won't be able to this stack this like this forever, but for up to like depending upon the function, you may be able to put this up to 8 times or 12 times, something like that. And the advantage of this design is that your latency will be a lot less. Like if you just give two functions in the Keccak, then you will get output in 24. Instead of 24, you get output in 12 cycles, right? So you are likely to get higher throughput in some scenario if a function has a more less critical path. But uh, but what happens if you just stack this function over and over again? You will have the very high critical path delay, and you won't be able to clock your FPGA faster. So this is not desirable. So this latency will be less, but it will consume higher area, and it will also it won't support the higher frequency also. So its maximal allowable frequency will be less. So this is not desirable in maximum throughput generation. So this is I think the worst design of all. So now today I'm gonna this is the design that today I'm gonna discuss in detail. This is the best favorite design for mining application in most of the algorithm. So we've got input over here, and we got register, and we have function, and we have got register again, function again, register again, function again, and we go on up until we repeat this register function block the number of that many number of times. Like for Keccak, we repeat this register and function 24 times. So there is new function for every iteration, every iteration, let's say. So the main advantage of this design is you can give input, and it will go over here in first clock cycle. In second clock cycle, it will go over here, and you don't have to wait until we get output. We can give input every clock cycle, right? So you get the uh, maximum throughput with this design, and it has less critical path also because we have used registers in every pipeline stage. So it will have less critical path, and that will make we will be able to clock the frequency or even overclock the FPGA, so to up to maybe 400 500 megahertz. So this is the most desirable design for mining application or some high throughput application. All right. So this is the combination of that pipelining and basic iteration. I won't go into much detail here, but in this case, we will be able to give input in every 4 clock cycle. So now I'm gonna show you how to write Keccak from scratch, almost from scratch, and get the highest throughput. Like we'll be able to get around 12,000 million as per second. Let's get started. Okay. There is I have already opened the project, and this is Keccak, and Krishna sir has already mentioned how to use this component and instantiate it. So I won't go into much detail here. Yeah, and you don't need to know what goes inside this component. That's not important. It's out of the scope of this webinar. Today I'm going to show you how to use this component, like instantiate it, how to use this component to get the maximum throughput. Okay, let's get started. First of all, you need all the signals to go for, like let's look at that. Okay, you need a register over here. So let's declare all these wires over here, and we have lot of wire in every register for input and output of the register. So let's declare some like we have got 24 registers, so we need for input and output of the register we need 48 such signals. So let's get started. Signal, let's say R in 0 and R out 0, and these are the signal for register in and out. It's a standard logic vector. In case of Keccak, this value is 1600. It has got 1600 bits. So this is a signal, and we need this up to R in 24 and R out 24. So I'll just use shortcut here, just Control D up to like 24 times. I think I got that. And just use over here, just use Alt and Shift and down arrow key. Alt, Shift and down arrow key, and you will be able to select like this, and just press Alt C, and let's start from 0 and increase by 1, and we're good to go. Yeah, oh, I got 35 of those. I don't need them. From 23 I can just delete it. Okay, and same with R out, and yeah. Okay, now I can instantiate sorry, I just used this begin here. Begin should be later. So let's instantiate that component. Component is let's UUT. You can use UUT, and that component name is round F. Round F. So this is one round of Keccak, and you don't need to know the details of it right now. And as you can see, the ports are clock and R in for R in, and R out, and round constant. I'll declare a round constant later, but these are basic. The basic way of instantiating the component. So we need, as you have already mentioned, we need 24 of the register. We need 24 functions too. So let's make it 24. Same process as above. Let's Control D. Maybe I've got that. And Alt Shift. I just need to write. I forgot the semicolon over here. Just insert semicolon, and I need R in 23 and R out. Same with R out. Okay, and I need round constant also. Now I need to declare the round constant, and for round constant you can just look at the Keccak official website, keccak.team, and you can just okay, maybe you can Keccak team spec summary. Okay, you can go there. The link will be in description, and you can see the round constant over here. This is round constant, and here's a secret to decrease the area. Like I'll just tell you some secret to optimize. You don't need to know. This will be different for different algorithms, but for Keccak you can see like these are round constants. If you look at closely here, this they have got similar pattern. Like there is a lots of zeros over here on these bits, and all these are redundant. We don't need all these zeros values. If it is deterministic, then we can optimize it. If it would be non-deterministic, like if it would be random numbers, it would be harder to optimize. So this is a bit easier to optimize because you can see some redundancy component here, and it's deterministic. So the you don't this would be if you we use normally, then it would take 64 bits, but it's already now but uh, as all these bits are redundant, we don't need 64 bits, and I will just use 7 bits instead. So let's declare the constant value for round constant. That would be RC, and that would be standard logic vector 7 bits, so 6 down to 0, and I'll need 24 of them. So just control D, and one of them, and that would be from 0 to 23. Right, and its value would be I have already stored this value C, and that would be, I forgot this. So I need to store, okay, and I need to paste that round constant over here. Okay, we've got some little problem while pasting it, so I'll just use it from, I have already written that constant value. I'll just use this from here. So yeah, okay, that's it. Now I need some, okay, that's we I'll just skip this also. All right, now we're good to go. So what I've done is just I have just instantiated all these rounds, and I have given the R in 0, R in and R out for all of them, right? This is single round, and this is another round. We have 24 of this all rounds. So from the presentation we can see what goes, like from the output of round 0. This is round 0, suppose, and from the output of round 0, it goes to through register, it goes to input of round 1, right? So let's make that. So and that happens in every rising edge of clock. That would be register. So let's make process, and that would be sensitive to clock, and begin. And I just need if rising edge of clock, then I just need R in is R in, R R in should be another, the R in of the second round should be R out of first round. So let's make this like this, and same as again. Control D, something more, and I'll just be the R in of first module should be, second module should be R out of first module. So 0. So here it is. The output of R out goes to R in rising edge of clock, and that's what we want. And we don't need all of this. And this end if and process, and we're good to go. So the Keccak is almost completed, but we need some little bit extra things, like we need to, the input here is 512 bit, but the state of Keccak works in 1600 bits, so we need to pair it before we pass it to these states. So I have got padder. This is constant. You can just paste it here. This is padder, and like we're just good to go. And one thing more, this Keccak has the Indianness of Keccak is different from the normally we use. We need to swap the bytes before we use for Keccak state. So for that, changing the swiping the bytes and changing the Indianness, we need another component called index relocation. We don't need detail. It's a simple function actually, but we won't go there. It's just swapping the bytes. So let's put that function also. Let's declare some signal first, and we are finished. Signal, like it should be padded, right? Let's call it is 1599 down to 0, right? This is padded signal, and for that padded we need some like padded should be a D in, and we just need to pad this padder, sorry, padder. So this is padder bits, and I just padded it to D in and to get this signal padded. That's it. Now I need to swap those bits. Let's call that name swap, and index relocation in is that, and I need to pass this padded value, and this value should be given to the input of this round, that is R in 0. So if we give first input from padded value, and it goes on, and this round will take on from there. Now I need to take the output. Output would be the first 512 bit of this round 23. So it should be this 512 bits of this round of this output. So that would be round 23. So let's keep that. And finally, we need to swap the bytes again at the final time also. So let's call it swap 2, and that should be index relocation in, and I forgot a port map. All right, in relocation in and port map, and that should be around R out 23. This is our output, and we need to change the Indianness, and let's call it final, right? And I need to declare that final signal also, padded and final, right? That's it. Like, we're good to go now, and let's create a test bench over here. Okay, this is test bench, and for creating test bench I'll just use the shortcut. So this is our code, and for test bench we can just go to this dollars site. We'll just link this in description. Just paste it and it will get that component initialization. Just put it like this, and I just need to paste it in test bench. Sorry. Okay, here it is, and I need to give the instance the d in some values. Let's give some input. Like I have some random 500-bit input data. I'll just give that, and let's wait for a 20 okay 1 clock cycle. We can give new input every clock cycle, so we'll get the maximum throughput possible. Okay, so this is waiting to 10 clock. Let's give another input. Let's just change little bit. Instead of 0, let's keep it 1, right? And just wait for 10 nanosecond, and just repeat this few more times. And instead of 1, let's keep 2. Instead of 1, let's keep 3, 4. And let's wait for 1000 nanoseconds more. So we're good to go. I'm expecting some error. Maybe we may get some error, but let's test. Okay. R24, I've got one more modules. You can just test it here. R24 is not declared. I just forgot 24. So here I must have some R24. I'll just declare. All right. 136. Sorry, I just made this extra. So yeah. And yeah. Okay, let's keep this over here. I need to change this to cell. Okay, sorry. Keccak 4. I'll just keep Keccak 4 its name, and its name is Keccak 4, I guess. And I'll just use this. I'll just disable it. Okay, we've got some output. Okay, let's test this. Okay, for example, we have given input here over here, and we are giving input in every clock cycle. We have not given much input, but we can test for a few times. Like this is our input, and we're getting output over here. and we're getting output. This is the main thing. Like we're getting output every clock cycle. You see, so this is getting the maximum throughput possible. Okay, and let's check input and output test. Let's check the input. Like this is our input, and the way to test is there's a website. I will link this website also in description. I'll just paste it over here and just select the Keccak and calculate. We are getting 7C08, something like that. And we must see same output over here. Like if we change the input to, like if we give this input, second input, and we paste it that over here, we're expecting the output to be 5 to E924, E924, something like that. And we're getting that output. So we're getting
Okay,
new
great.
output
So this is so great.
every
So
clock cycle.
Jagannath have started
Uh,
from the scratch and he's
yeah,
also saw the simulation.
yeah.
So that's great. So guys, you already know the basics of Keccak, and actually we have the sessions on AES,
Mm,
and we would like to have that AES session in next one. So our 60-minute time has been up. So guys, thanks for your time and the participation, and we are thankful to Jagannath. He is showing from very much scratch of Keccak to the simulation, and he verifies the results. And what is the hash rate currently we are achieving with Keccak
okay.
Jagannath?
Okay, this single instance, okay, will result in 600 million as per second. But the plus point of it is this is getting utilizing around 4% of high-end FPGA board of BC, like BCU
Wow,
1525.
that's really nice. Yeah.
Yeah,
So
yeah,
we
it
are
will only.
consuming too less resources.
Yes, to get, and we're getting 600 million hash per second if we calculate. Like we are getting every output at every clock cycle. That means
Hmm.
we can get the like we are getting the equal hash rate as the clock rate of VCU or some high-end boards. And as high-end boards can support up to 600, 700 megahertz. So we are getting
So
like
that's really
yes,
great.
yes. And
So
so we
guys,
can,
thanks for your
and
time.
one point is like we are getting using only 4% of the resources with such extreme hash rate. So we can multiply use
Hmm.
this instance multiple of times. Like for if we
Yeah.
are using 4%, like we can instantiate it, all this block 25 times to get the
Yeah.
utilize
Great.
100%.
Hmm.
That would
Hmm.
multiply the hash rate 25 times also. So we can get
So
12
that will be
gigahash
for
or
like how
13
much?
gigahash per second. Ajay? Yes,
Okay.
that
So
will
what will be
result
the
in
total
12
hash
to 13 gigahash per second. 600
rate?
million hash
Okay.
per second times 25 equals like maybe 15 gigahash per second, something like that. So we
Okay,
can get that.
that's really great. That's really great.
Yeah,
Okay. So it's really nice to have this type of real-time simulation also. So
yeah.
Jagannath, thanks for your plan
Okay,
and
thank
thanks
you.
for your everything you are showing up.
Yeah, yeah, yeah,
And
yeah,
we would like to close up this session. So thank you
yeah.
for everyone for participation, and we'll also have this recording in the corresponding email, so you guys can also watch the recording, complete recording, and if you have any queries, you can just write us to info@logictronics.com or the email which we have provided on email. So guys, thanks for your time. We would like to stop the session
Thank
and
you.
meet you in next similar session.